Bismillahirrahmanirrahim. Assalamu alaikum. So we have seen the contour in the complex plane is nothing but a piecewise smooth curve. So if we have a piecewise smooth curve, then we can call it a contour or a path. Now our task is to define contour integral in the complex plane. So contour integral. So I will explain how to define the notion of this contour integral. In other words, the integral of a function of complex variable with respect to complex variable over a contour C. So I will put forward the definition for this quantity. This goes on the following lines. So suppose f, which is depending on a complex variable, is a continuous function on a smooth curve C parameterized by z of t to be x of t plus iota times y of t. This where t is running from a to b. Then my complex integral over a contour of complex valued function is given by integral from a to b of f of z of t multiplied by the derivative of z with respect to t dt. So if you wish to find out or you calculate the complex integration of a complex valued function with respect to a complex variable on a contour, then all you have to compute is to compute this integral. And of course this integral looks like the integral of a complex valued function with real variable. Let's solve this example where I have to calculate the complex integral of the function f of z to be conjugate of z. So my function is f of z to be the conjugate of z over the contour or the curve, and the curve is defined by this way. So my curve is z of t equal to 3t plus iota times t square, where my t is running between -1 and 4. So we have to compute this integral. So recall the formula. The formula says that you have to calculate from a to b the integral of f of z of t multiplied by the derivative of z with respect to time dt. So let's now compute first the f of z of t. So my f of z of t is going to be equal to z of t conjugate. So you know that the z of t is 3t plus iota times t square conjugate. So when you evaluate the conjugate, you already know that you change the sign of the imaginary part. So it turns out to be 3t minus iota times t square. So this is f of z of t. Now I need to calculate the derivative of z with respect to t, because I also need to calculate this quantity. So z of t is equal to 3t plus iota times t square. So its derivative is going to be 3 plus 2t iota. So I have differentiated this function. So now my task is going to be to multiply these two quantities with each other, and this will give me this product integrand, and then I will finally integrate it. So let's now put it into the integral a to b f of z of t times the derivative of z with respect to t. So the limits are from -1 to 4, and my f of z of t is 3t plus iota times t square, and I have to multiply this with 3 plus 2t iota dt. Now let's multiply these. Minus 1 to 4. This multiplication turns out to be 9t plus 6t square I and plus 3t square I, and then minus 2t cube. So this is just complex multiplication, right? And then it turns out to be, we have made a small computation mistake, so here we have minus over here, right? So if this is minus, then I will see the changes over here. So this is going to be the minus 3t square, and this has to be plus 2t cube, right? So this was small, mistake. And my integral from over the contour of f of z dz is going to be equal to minus 1 to 4 2t cube plus 9t plus 3t square iota dt, which can be written as minus 1 to 4 integral of the real part and plus integral of the imaginary part. So then you have to compute this, so I can apply the properties of integral over linear combination, minus 1 to 4 t dt plus iota times 3 minus 1 4 t square dt. So then 2, and then this is t power 4 1 over 4 minus 1 to 4 plus 9 times t square over 2 minus 1 to 4 plus 3i t cube over 3 minus 1 to 4, and now you substitute these values of t. So this is going to be 1 over 2 times, when you substitute 4, so you will get what when you will put the limit, you will get 256 minus 1 plus 9 by 2, 16 minus 1 plus iota times, so t cube is 64 plus 1. So this is just putting the limits. So you will get what you will get 195 plus 65 times iota. So this is the answer to this integral. So this was the all about computing a complex integral, and we solved an example as well. We will move ahead later on with other examples. Let's move towards solving another complex integration example. So I want to integrate over a contour the function 1 over z with respect to z. So I have a function f of z which is 1 by z, and I want to integrate with respect to z. So it is an example of complex integration where my curve c is defined by x to be cos t and y to be sine t, with t running between 0 and 2 pi. So in other words, it's a unit circle centered at origin. I can write down this x equal to cos t and y equal to sine t in the parametric form, which is given by z of t to be cos t plus iota sine t. But using Euler identity, I can also write it in the exponential form, because I can write a complex number in the exponential form by e to the iota t. So this is the complex exponential form of my z to be cos t plus iota sine t. Now what I have to do, I'll solve this integral over this curve, right? So let's solve. So I'll write down the formula, and the formula says that if you want to integrate a complex valued function over a contour, then its integral is given by a to b f of z of t times z prime t t. So where z is of course the parametrization. So in our case, f of z is 1 by z, and in this way my f of z of t means I will substitute the value of z of t, which is this, over here. So I will get 1 over e to the iota t. In other words, I can write e to the minus iota t, right? And then I can substitute the value of f of z of t and z of t, the derivative of z of t. So I need to calculate the derivative of z of t. So you know that z of t is e to the iota t. So when I will differentiate, so iota times e to the iota t. Now I can substitute uh, these values into the formula, and I'll solve my integral. So c f of z dz is equal to a to b f of z of t times the derivative of z dt. So my a is of course 0 and b is 2 pi, so 0 to 2 pi. I'll integrate. So f of z of t is e to the minus iota t, and my z prime is iota times e to the iota t dt. But when you simplify this, you will have 0 to 2 pi, it's just iota dt. So when you will integrate this, so it is iota, which is constant, you can snatch it outside, 0 to 2 pi dt, and this is just your single variable calculus integral. So iota times 2 pi, so it is 2 pi I. This is the answer to this complex integral. So let me just explain without solving the properties of contour integral. So these are basically the same properties that you have already seen in your calculus 1, uh, 2, or any course where you study integrals, because these are some of the properties which remain same for all kinds of integrals almost. So the first property is saying that if you're integrating a function and you have a constant multiplied to it, then you can snatch your constant outside and you integrate your function. So it's basically the scalar multiplication property in the sense of linear operators. And the other one is if you are integrating a sum of two functions, then you can integrate and sum. So integral of sum of two functions is basically sum of integrals of two functions. The third property says that if C is a curve which is joined by two curves, so like let's say this is C1 and there is another curve C2, so these two curves are joined, and you name this whole C1 union C2 a new curve C, then you want to integrate your function over this C. What you can do is basically you can integrate f over c1 and integrate your f over c2 and add. So the result is going to be the integral of f overall over the whole of the c. So this is how it works. The fourth property says that so if you are integrating a function of complex variable with respect to a complex variable, so over minus c, so minus c denotes the curve having the opposite orientation. So so if a curve is oriented this way, let's say, and you have integrated it, you know and then you take the integral, but you change the orientation. So in that case what will happen is you will have this property. So if you change your orientation, you will have minus times the new integral, right? Or let me restate it. So I have integrated a function over this curve c, right, of f with this orientation. Now suppose that I am integrating with this orientation, so like the minus cf. Okay, so what will be the difference between these two integrals? So one is going to be minus times the other, right? So these are four properties which I haven't proved, but I have just stated these properties which we will be using throughout our next sessions.